Thank you very much for having me. It's fun to be back here. There was a period, I think I came here like 3 out of 4 summers, like between 2005 and 2009. So I spent a lot of time here, but I haven't been here, I think, in a while. So it's really nice to be back. Thank you for having me. This kind of we'll see how this works. This is gonna be a weird talk. It's different than I've given before, and then it's gonna be a very general talk combined with a very specific talk. It's gonna be focusing more on the general. So in some sense, in general, this is going to be my thoughts about how to think about empirical work from a very eagle's eye point of view on things. I want to talk. There's a whole bunch of terms. There's a whole bunch of terms that we use in empirical economics and econometrics that I think mean different things to different people that I want to talk about. I'm not going to tell you the right definition, but I at least want to be explicit on what I mean by them. So structural, reduced form, design-based, identification, exogenous. All those words I think mean different things to different people. So I want to think. I'm going to formalize things a little bit and tell you how I think about things. I want to think about advantages and disadvantages of different approaches, and mostly advantages and disadvantages of quote structural versus quote design-based research. And then finally, I want to talk about indirect inference, which I think is a nice way of combining some of the advantages you get in thinking about identification from design-based stuff, but the ability to answer policies that have never been implemented before that you can get with structural estimation. And then I'll give an example of that, which is a new paper, not even a paper yet, but it's something that we've been working on, estimate the dynamics of college entry. The amount of stuff spent on the empirical work is going to be relatively small. I also don't know how long this is going to take. So you might be here for 3 hours, and you might be here for half an hour. We'll see. I'm never very good at figuring these things out. Okay, here's how I think empirical work is done, and I don't know if it's, you can either interpret this as my impression of how empirical work is done or how I do empirical work. I am comfortable in saying that when I think about empirical work, and when I train students, I try to tell them to think about these things as basically 5 different steps. Step 1 is write down the model, and by the model here, I'm going to mean the data generating process. So be explicit about that. It might be complicated. It could be pretty simple, but be clear what that is. Think about identification of what you want to identify within the model. Find an estimator that's going to give you a consistent estimate of that. Estimate the model and show the results. The main part that I'm going to talk about is really the first 2 parts, or what I'm going to spend a lot of time thinking about before we get to the estimation. So I want to think about writing a data generating process, and I want to think about writing it in very broad terms. So we can think about xi is going to be exogenous variables that are observable to the econometrician, have some distribution h. Ui is going to be unobserved variables that can potentially be correlated with xi. They're going to be known, f is going to be known up to parameter theta, and then we're going to have some outcome. So epsilon is going to represent the outcomes, and that's going to be some function of the observable, the unobservable, and some parameters. The parameter space doesn't have to be finite. You can think about this non-parametrically. If you think about you think about theta as an infinite dimensional parameter space. I'm thinking about, be clear, I'm thinking about these things as they're generally all very high dimensional. So there could be lots of x's, lots of u's, and lots of epsilon. So you might want to think about xi and ui as the exogenous variables that you enter with, and you might think about y as the model. So this is what's producing things, and you might think of epsilon as the endogenous variables. So these are the things that are being produced by the model. And I want this to be very general, so that if you have multiple equilibrium, somehow if you want to the data is going to have to decide between the various different equilibrium. That's going to be part of y. So I want to think about y as a very general concept at this point. I also think that epsilon is an underused Greek letter in economics in general. So I also want to get people to use epsilon a little bit more. So yeah, I guess I said most of this. So we can think of this non-parametric. So for example, we could think about the distribution of the unobservables as completely non-parametric, and we can think about the parameter space as a finite set of parameters theta 1, and then the distribution f large enough. And I said this as well. So think about this can incorporate equilibrium. It can incorporate multiple equilibria. It can incorporate dynamic programming. So complicated structural models we can all think about within this. So I don't want to think about the details of what that model is. I want to think about what we're going to do with it. So like here's an example. Let me give you the first classic example. Here's a simultaneous equations model. We have a supply curve and we have a demand curve, and then we know the distribution of the expected value of u and v conditional on the x and the z is going to be 0. To put this in the notation above, we would think is a classic way. The x is going to be x and z. The u is going to be the two error terms. The endogenous variables are going to be prices and quantities. The theta is going to incorporate all of the standard parameters and the joint distribution of u and v. And then I can write the data. The model essentially by this, which is something very close to the reduced form of the model. So we can think about that as how prices and quantities are determined. So nothing new here, just to show you how this fits into our model. I almost never give a talk without talking about the Roy model at some level. So I feel obligated to talk a little bit about the Roy model. So I'm going to put the Roy model into this. Yeah, I guess one of my first, reading Bo's paper with Jim Hackeman was one of my first exposures to the Roy model at a young age. Actually, I have a copy of that paper, like a draft from like 1980. It was like 1986 or something like that, like well before it was published. It was kind of cool. I don't want to get rid of it. Anyway. So in this model, we want to think about the labor market. The labor market is going to be a village, and you only do two things. You can either be a hunter, you can be a fisherman. You're going to be paid a piece rate, depending on how many fish you catch and how many rabbits you catch. So your wage is going to look something like this. Your wage as a fisherman is going to look something like this. Your wage as a hunter is going to look something like this. The UFI and the UI, now it's a generalized Roy model, so I'm going to allow people to care about things other than just wages. So my utility is going to depend on the wage, as depend on some non-pecuniary aspects of the particular job. I'm going to choose to fish if the utility for fishing is higher than the utility from hunting. I can observe whether you fish, and I can observe your wage, which is going to be your fisherman wage if you fish and your hunting wage if you hunt. Let the joint distribution of all four error terms be G. And then in this case, the endogenous variables here are going to be whether you fish and your wage. Then you're going to have the standard x's, the epsilons. That's going to be the theta, and then this is going to be the outcome. I partly want to do this because now I want to think about the potential outcomes model. And the potential outcomes is essentially a special case of this model. And partly I want to talk about that because we often think about, well, you can put structure on the model, you cannot put structure on the model. The potential outcomes model is putting a fair amount of structure onto the model and is being relatively careful about what the data generating process is. So even though we think about this as not specifying anything, the potential outcomes model, it's essentially a special case of this where, whoops, I went back. Where hunting is like treatment effect 0, fishing is like treatment effect 1. Whether you fish is the dummy variable for whether you get the treatment or not. Here, the potential outcome yi1 is essentially the error term. Right, so I'm going to put this in my model as the error term. The potential outcome yi naught is also going to be error term. The yi is going to be the wage, and then the outcome equation is going to be determined by this, which isn't exactly the generalized Roy model, but it's very close to the generalized Roy model. So we can think about the potential outcome. I can put the potential outcomes model into this framework in the following way. Okay, so even when we're using something like this potential outcome model, we're getting into definitions of what these things mean. We're still putting some structure. We're taking seriously that this is what the data generating process is in order to get the late as something that we're estimating. Okay, that's the first thing. And now I want to talk, there's another word which means like totally different thing. Not totally, there's a little bit of relation, but the word identification to a design-based person is almost completely different than what is meant by identification to econometrician. They're related, but they're not identical. What I'm going to take here by to mean identification, the thing that I'm going to use, well, let me say this first. I think one major criticism of structural work is that it's not identified. And often we think about the design-based stuff as the identification revolution. What does that mean, and how is that related to the formal econometric definition of identification? I think it's not necessarily that closely, it's related, but not that closely related. I think when people say structural work is, and I'm sympathetic to, like, I want to be clear here, I'm giving this talk as somebody who appreciates both structural work and design-based work. I tend to do structural work because it's sort of where I think I have my comparative advantage, but like as mentioned, I was an editor at Joly, and certainly when I was the editor of the Journal of Labor Economics, the majority of papers that I published were design-based papers. So this is not a structural person that's trying to dump on design-based stuff. It's somebody who's trying to look at the best, think about comparison, and think about the best of both worlds. So I think what people mean when they criticize structural work, and both of them are fair, I think the criticism number one is it comes from functional form. So the thing is not really well identified. The identification comes not from some fundamental property of the data, but comes more from the functional form that you chose to write down. And often that for a lot of papers, I think that's fair. There's another one which is sometimes fair and sometimes is not fair, which is it's not so much that the model is not well identified. The problem is it's difficult to understand where identification comes from for the reader. And this is an experience I've had in sometimes you write models, you spend 15 years estimating the model, you spend times playing around with the model. I know where identification is coming from. From the person that's playing with the code and playing with the data, I completely understand where it is. I'm totally sympathetic that the reader of the paper does not understand where it is, because they're not spending 15 years playing with the code to understand it. So I think that's fair, and I think that's a challenge that we're trying to deal with, and I don't know exactly the best way to do it. But again, another advantage that I'm going to point about indirect inference is that I think it makes identification more transparent. Okay, so I guess what I'm saying is I can think about one of these is a fair comparison, which is saying it really isn't well identified. That is, identification is coming from assumptions that we don't like. The other one is identification is not transparent. Okay, that's different than saying it's not well identified. It's just saying I have trouble understanding where identification is coming from. And this is something we can do a little bit of something about. So I want to define identification here. I'm going to use I'm not going to be as formal as Rosa Matzkin, but basically I'm going to use Rosa Matzkin's definition from her 2007 handbook chapter. An important thing, like the econometricians in the room, this is going to be obvious. To non-econometricians, maybe it's not, but identification is a population characteristic. It has nothing to do with the sample. The identification question is, if I observe the whole, if I observed the sample, the population version of the sample, could I uniquely tell what that parameter is going to be? That's what identification is. So people in the seminar, when they say the model's not identified because your sample's too small, is something that, like with this definition, it doesn't make sense, though I do understand what they mean. So point identification of the model, basically it's a relatively simple idea. It's what are we going to observe in the data? If you think about the data generating process, there were three things. There was an X, there was an upsilon, and there was a U, and I told you that U was not observable. So what can the econometrician observe? We can observe the joint distribution of X and upsilon. Okay, so the best we could ever hope to do is observe the population distribution of X and upsilon. So what does point identification mean in this model? Point identification means that there's only one value of theta that could have possibly generated that joint distribution of X and upsilon that you mean. So a little bit more formally, if you let theta be the full, whoops, keep messing this up. Let theta be the parameter space. If theta is the true, if theta naught is the true value, if there's any other theta 1 that yields exactly the same joint distribution of X and upsilon, the model is not identified. If there's only if there are no such theta 1, then the model is identified. Okay, so that's point identification. This morning I got rid of this slide and then I put it back in because I kind of needed it for the next slide. Set identification is just saying if there's multiple values of theta if there's multiple values of theta that can yield the same observed data, then what you can identify is the set. So you can't tell which member of the set it is, but you can identify the set. So another way to think about point identification is your identified set is a singleton. Okay, here's the next thing that I want to think about, and this is going to be a little bit of another. This is not explicitly the difference between structural work and design-based work, but it's closely related to the difference between structural work and design-based work. Often when we're estimating structural models, we're thinking about identifying the whole model. We estimate the full model, and then we use the model to simulate something. Most design-based work, you're not interested in identifying the full model. You're identifying some feature of a model. Okay, so formally, let this psi of theta. So if you knew theta, you would know psi. Let psi of theta be some feature of a model. Let the identified set of psi be defined that way. Any psi of theta for theta in the identified set. Point identification of psi is going to occur when psi of I is equal to that object. Okay, this is often going to be very interesting because there's lots of cases where the full model is not identified, but a particular feature that you care about in the model is identified, and then you can focus on estimating that feature rather than estimating the full model. And again, this is one major difference between the way that people that estimate structural models do things versus the way that people estimate design-based things. So examples of features are a mean, a regression coefficient, elasticity supply would be an example. The effect of a policy is an important one that we might care about if we're evaluating a policy. And then I'm going to highlight the local average treatment effect. So if you're doing IV, and you're estimating the local average treatment effect, typically in the IV case, especially if you have limited support in an instrument, so if you only have a binary instrument, the full distribution of potential outcomes is not identified. That full model is not identified. However, the local average treatment effect is, okay? And in some cases, in the most limited cases where you have a binary instrument, in some sense, the local average treatment effect is the only thing the only treatment effect that's identified, the only causal effect that's identified. So again, this is a little bit of a difference between the approaches. One is thinking about identifying the whole model. The other one is thinking about identifying a feature of a model. Okay, here's what I want to talk about. And partly why I introduced all this notation is I want to think. I'm going back to sort of Cole's Commission from the 60s and how they thought about econometrics and how they thought about structural models. And to me, this is really the classic definition of a structural model. That the point of a structural model is to estimate the effect of a policy that has never been implemented before. Okay, so that's going to be fundamentally different than evaluating a policy that we see in practice. So I'm going to modify, I want to modify this notation of the data generating process. The X and the U, I mean, you could allow the policy to change them, but that's not that interesting. What we're usually worried about is the policy is going to enter the model and is going to change the way that these things work. So now there's going to be an upsilon that depends on the policy parameter. The problem is we don't get to observe this data generating process. We don't observe the data generating process on policy pi because pi is something that's never happened. We've never seen it. It's something that we want to simulate. So to fill out the notation, let me introduce this just let this be the current data. So theta pi naught is the policy regime that was in place at the time the data was generated. So this is going to be your data generating process, the data that's generated under the process that you see the data, while this other alternative, this one here, is going to be what will be happening in the alternative regime after the policy is identified. Okay, so now we can think about identifying a feature, but the feature that we might want is going to be the effect of implementing this policy that we've never seen before, right? So this is a parameter that we're interested. The next part is going to be a little bit loose, but I could formalize it. If I wanted to. But if I think about identifying psi of theta, it really requires two different assumptions. The first assumption is that I can identify theta, I can identify the model from the current data regime. Okay, so from the current data regime, I can identify theta. That's the first thing that I need. But then the second thing, which is almost the classic definition of structural, this is almost what I like to think of as the definition of structural, is that the policy counterfactual is known up to parameter theta. That is, I can specify the data generating process, this thing, so that if I know what theta is, I know what that object is going to be. And that requires a few different things. One is it requires that the theta that enters this thing is the same as the theta that enters that thing. Right? It's the same set of parameters. So there's some set of parameters that you need to know to simulate the structural model, but you can't identify those parameters from the current data generating process. The policy counterfactual is not going to be identified. Okay, so that's the first thing that you need. The second thing you need is the policy data generating. I mean, it's I don't know if this is a different thing or a different way of saying the same thing, but you need that the data generating policy is policy invariant. Or a different way to say it is, if I know pi is sufficient to tell me how the data generating process will change when I change pi. Okay? That there aren't other things that are going to change. If you're coming from the design-based world, you've heard that assumption before, that's essentially what the Sutpha assumption is in the potential outcomes thing or the late thing. So what does Sutpha stand? I don't remember what it stands for. Stable unit treatment. Yeah. So that's basically that is basically a structural assumption. Right? There's some level at which, if I think about the definition of structural as policy invariant, the Sutpha assumption is essentially saying that the potential outcomes framework is structural. It's policy invariant. Okay, so that's a sense in which these really, the structural versus the most design-based thing that we think about in the world is in a very large sense structural. We're making real structural assumptions that we need it. And again, at some level, this is the classic definition of the word structural. This is a quote. I'll let you read the quote. This is an awesome quote from Frank Knight, and you can kind of see how it relates to things, right? So the world's not very interesting if we know the future already, but if the future looks nothing like the past, then we're screwed. So we need something like this theta that allows us to say how the past is going to relate to the future. Here's sort of classic example of this would be the simultaneous equations with taxes. So I have a model where there's no taxes. Now I want to impose a new tax when people buy the good. I know exactly how the point is I know exactly how taxes are going to enter the model. What's going to matter when people buy the good is the after-tax cost of the good. Okay, I know how the seller is going to respond, and therefore, if I estimate the structural model, if I know all of the structural parameters in the simultaneous equations model, I can tell you the effect. I can tell you the effect of the taxes. Okay, so this is sort of maybe the classic example of this thing, but you can see where the structural assumption is important, right? What you're fundamentally assuming is that what matters to consumers is after-tax prices. So under the assumption that it's what matters to consumers after-tax prices, if you can estimate this model, you can estimate the policy counterfactual. Here's a bunch of other examples of policy counterfactuals that people have estimated in the last few years. The first one is the paper that I'm going to talk about briefly at the very end of this talk. Okay, so what does structural mean? And I kind of told you, I mean, I would say there's probably more than that. Like, I'm sure you guys can think of more than three, but here are, I think, three common definitions of structural. You can see how they're related, but they're not exactly related. First one is what I think of as structural means that the parameters are policy invariant. To me, this is the definition of structural. And notice that if that's your definition of structural, then whether your model is structural or not depends on what the policy counterfactual that you have in mind is, right? So if I'm thinking about people's demand for cigarettes, and I want to think about whether if I increase taxes on cigarettes, what's going to happen to demand, I'm going to take the preference for cigarettes as structural. Okay, and that's going to be a standard thing, and you wouldn't object to that. However, if I'm thinking about a preschool program where I'm going to intervene and try to convince people that smoking is bad, I'm changing preferences, and for that particular policy, that would not be a structural model because it would not be policy invariant. I think if I didn't think preferences would change from intervening, I wouldn't bother to intervene. Okay, so that's sort of, to me, the classic definition. That's what I think it is. I think most people mean this. We talked at dinner last night. I asked Mikkel and Runa what their definition of structural is, and this was the answer that Runa gave. Mikkel was too much of a wimp to give a really precise answer. So often this is what we mean. Often when people talk about a structural model, they mean somebody's got to be maximizing something. Like either you have a worker that's maximizing utility, or a person maximizing utility, or you have a firm that's maximizing profit. For some macroeconomists, that's not even enough. You need some sort of equilibrium to really make this structural. If there's no market, it's not really structural. So often when we think about these things, often in practice, this is what this term is meant to mean. And I don't want to say you should call it my thing and not something else. I just want to point out that these are different things and they mean different things. But you can see how they're related. Because typically, I mean, if you're really pushing things hard, you might say the only things, your preferences are like the only thing in the world that's policy invariant. Everything else can change, right? But we don't think preferences are going to change, except for maybe very specific examples of policies where we might think about preferences changing. So it's different, but it's different. It's different than this, but it's related to this. But from my view, it's a little bit too strong. I think that you can write down a structural model that you can use to do policy counterfactuals that's not explicitly somebody maximizing something. Another example, the structural parameter simultaneous equations. I added that. I don't know. A lot of people, when their definition of structural and reduced form, they learn in the simultaneous equations model. It's well defined there. Everywhere else, it's not. It's just sort of this fuzzy thing that people throw around. So maybe we all agree that the structural equations in a simultaneous equations model are structural. What does reduced form mean? Like, we used to agree that the structural parameters, we used to agree on this, that the structural parameters in the simultaneous equations model were structural. Therefore, the IV was the structural thing and the regression was the reduced form. But now people use reduced form to refer to IVs. Reduced form, I'm going to, here, the structure I said you can call it what you want. I tell you what I mean by it. In talking about this, we can talk about what we mean by it and be explicit. Reduced form is something that I want back. I think the word has become to mean, the word, it's two words. The phrase has come to mean something that it's different than what it originally meant, but the original meaning actually had content. So the original meaning of a structural model, and you can see it in the simultaneous equations model, you start with a structural model and you reduce it to the reduced form. So to me, a reduced form is you start with a structural model. The reduced form is a known function of the structural parameters. It's not necessarily invertible, right? So in a classic case of the simultaneous equations model without exclusion restrictions, I can write down what I can estimate the reduced form parameters. I know that they're a functional I know that they're a function, and I know it's a known function of the structural parameters, but I can't figure out the structural parameters from the reduced form parameters. That's what it means. I think it's useful. There are cases in which you can do policy counterfactuals with reduced forms. You don't, and you still need to write down the model. In order to for it to really be a reduced form, you need to write down some structure, but it's useful. There are cases where using things as reduced form is useful. So I guess a lot of these things I'll say, call it what you want. Reduced form, I guess I can't stop you, but reduced form to me has a well-meaning thing. If I want to think about design-based estimation is something that I think is a better way to think about. I mean, you know what I mean, I think, and these are what we mean by this. I guess mostly harmless econometrics techniques would be what I would think about as design-based things. These are the big 4 stars, favorite things that people use. I like the term, it's not that I particularly like the term design-based, but I like the fact that it has a well-defined term because it's different than a reduced form. I think a reduced form means something. And it's also different than, it's also, actually I'm going to say this in a way that I think some of my structural colleagues, people, not necessarily my colleagues at Wisconsin, but structural people in the world might say things like, well, these are just descriptive things. They're just data. We're just taking the data and we're doing something with the data. That's not right. And it's not right in a way that I think that I thought about formalizing before, that I can write down a data generating process, I can define a feature of the model, and I can show that this identifies a causal feature of the model. It requires some structure. It requires writing down the model to show this. So it's not descriptive. These are formal properties of well-defined data generating processes. So I like the term design-based estimation to think of these. Okay, the next thing that I want to do, yeah, I guess I said this. I said all this, though. There's one, I mean, some people do design-based stuff and they don't want to take a stand on what the data generating process is. I get confused. Like, maybe it's just me and how I was trained to think about it. I guess it's obvious from the way that I said I do empirical work is I start by writing the data generating process. If you want to tell me how you estimate something without telling me what it is you're trying to estimate, I get confused. But I think that the vast majority of work in econometrics does this. Formalizing design-based work requires being explicit about what the data generating process is and being explicit about what it is that you're identifying. Okay, so now in very, is there a clock? What? 5 to 3. And what time did and I started at 20 past. Okay. Well, yeah, this will be about an hour. We'll see. Yeah, unless I start talking about how long it's going to take and keep asking the time. I want to talk about advantages and disadvantages of structural models. I want to make two things clear before I do this. I mean, this is not, again, this is not just a structural guide dumping on design-based stuff at all. First of all, there are advantages and disadvantages of each. The fact that there's disadvantages in each makes them complements, not substitutes. I mean, in my view, what we're doing is hard enough. Fighting about which method to use, I don't think is very fruitful. There's some things that are designed better to answer some questions, and there's some things that are designed better to answer other questions. Both kind of questions are interesting. The other thing that I want to make is I'm doing this at a very broad level. There's a lot of what I'm going to call advantage of a structural stuff. There's lots of design-based stuff that does a really poor job of that, and a lot of stuff that I'm going to call, the other way around. A lot of stuff I can call it advantage of structural stuff. A lot of design-based stuff might do a much better job than some of the structural models. So these are very broad terms. I'm not making this claim about all structural work or all design-based stuff in general. But here's how I would generally think about the difference between the two. I think in general with structural work, there's more emphasis on external validity. And that's almost by definition, if you define structural as estimating the full data generating process, and you define design-based as estimating a feature of the model, that's almost true by definition. So that typically structural models, there's to be a little bit more emphasis on external validity, design-based more estimate, and maybe even a lot more emphasis on internal validity. Structural models, you're estimating the full thing typically. So typically it's going to be complicated, and there's going to be lots and lots of parameters you're trying to estimate. An advantage, an advantage of design-based stuff is usually you're focusing on a single parameter or a very small number of parameters, which is good and bad depending on what you're trying to do. The identification thing, like which one is, and I think of two sides of identification. There's one that, and the side that people on the design-based are going to focus on is the map from the data to the parameters is much more transparent. And that's clearly true. It's very clear, if you're doing a regression discontinuity, I understand exactly what's going on. Like the map from the data to the estimate is, you draw me the figure, I can see exactly what's going on. So that's a big advantage of design-based. I think the advantage of structural is exactly what the parameter itself means is much clearer in a structural model. And maybe my friends that are super structural might say, without the model, I don't even know what the parameter means. It's just something. I need a model to be able to interpret what this means. So advantage, you're trying to estimate the effect of a policy has never been used. I would, one thing that bugs me is when people estimate design-based stuff, they say I'm estimating design-based stuff, not a structural model, and then they do a back-of-the-envelope calculation at the end of the paper, which is essentially it's something like a structural estimation, and you're pretending that you didn't make assumptions, but you did actually need to make the assumptions in order to do that. But you often didn't bother to write them down. One advantage of the structural model is that you need to formalize the conditions that justify the conclusions in your paper. An advantage of design-based advantage of the design-based thing is that it generally requires fewer assumptions in order to do what you're doing, and certainly to estimate it. Advantage of structural model, like sometimes it forces you to think about what the data is and how to think about the data and how to interpret the data. I think the design-based people might say, well, that's true, but maybe you're wrong. Maybe the data came from somewhere else. So you're thinking about the data in this way because your model says that's what it is, but in fact, it's completely different. So anyway, that's a very broad terms. How I think about the differences between structural and design-based stuff. Now I want to think about, I don't know whether to call this estimation of the structural model or estimation of the data generating process. In general, the way that typically people do structural estimation is I estimate the full model, and then after I estimate the full model, I simulate the things that I'm interested in doing with the model after estimating it. So typically with a structural model, that's what we do. So when we think about estimating the structural model, you're not really estimating, you're estimating the data generating process. Okay, so I'm calling it estimation of structural models, but it's really sort of broader than that. I'm thinking about estimating a data generating process. In not all structural models, you have to identify the data generating process, and you can think about identifying the data generating process when it's not a structural model. So these are not perfectly related, that this is not exactly structural versus design-based stuff, but it's what we typically do in structural stuff, and we typically don't do when we do design-based stuff. Okay, so we want to estimate the data generating process, and there are there are basically two different ways to do this in economics, in econometrics. One is going to be maximum likelihood, and then the other is going to be GMM, or indirect inference, or simulated method of moments. I'm going to kind of group those in together. So those are the two main things. If there's something else that I'm not thinking about, let me know. But those are the two main things that I think about. You know, maximum likelihood. You all know. You write down the density of the model. The likelihood. You know, the likelihood is just that you write is a function of the theta rather than a function. It's a function of theta given the y rather than a function of the y given the theta. You estimate the log likelihood. And the nice thing about maximum likelihood is it's efficient. So given the model that you wrote down and the data that you have, this is the best you could possibly do. So this is going to be your most efficient your estimator of theta. A problem and this is going to be important, a problem in estimating likelihood is this integral problem. So generally, your likelihood is going to be a function of the observed data. To get this likelihood, you have to integrate out all of those unobservables. Okay? And integrating out all of those unobservables can be really tricky and can take a very long time, particularly if solving this why not involves solving some complicated dynamic programming model or solving for an equilibrium. Doing that and doing the integration is harder. So one advantage that I'm going to talk about a bit about indirect inference is a way in which it can be a lot faster than maximum likelihood. And the reason, you'll see the reason from this. I can do often another way that I can estimate, notice that this is an expected value, so another way to get the expected values I can simulate. So I can draw S draws from U, and I can simulate this probability, which is just the likelihood. So this would be simulated maximum likelihood, which is sometimes easier to do if the density of U is some complicated thing that's hard to simulate it. Notice, and this is going to be important, what you need for this to work is you need S to be big. You need the number of draws that you have to be big. And often very big, because there's some chance that you never draw the particular observation that you see in your data. So if your model is complicated and y is or epsilon is a high-dimensional object, then there's a good chance that you never draw a set of u's that approximate that. But you want the set of times you draw that to approximate it to be large. So S needs to be really, really large. Okay? Not only that, you're drawing these large things for every single observation. For every single person, you need S. So I'm going to simulate the model for person number 1 in the data. I got to simulate S values. Now I get to person number 2. I got to simulate another S values, and S has to be really big. Okay. So this is where. Okay. So think about, keep that in your mind, and now I want to contrast that with simulated method of moments. So another way to estimate the model is by GMM, simulated method of moments, indirect inference. Exactly what these mean, exactly what the right terms are. Maybe I'm being loose, but here is how I think about those things, and I don't necessarily want to distinguish between them that much. So standard GMM, we write down the moment. This you should all know. We write down the moment condition. The set of thetas are the values for which the moment is equal to the moments are equal to 0, and we choose theta to maximize that weighted average. So that's GMM. Simulated method of moments is where we're going to get sort of this nice computational advantage that's going to make things feasible. So here's what I can do. Let me take any function. Let me take the data. So my data are epsilon and x. For any realization of epsilon and x, let me take any function of that data, and then let me take the expectation of that function of the data. Okay? So I have this expectation of the function of the data, and then once I do that, I can write my moment condition in the following way. I can get this g here and minus the expected value, minus the expected value. That thing should be equal to 0. Okay? So what? Why is that interesting? This is actually really cool. And here's why this thing is really cool. If I'm going to simulate the true value, that is, if I want to get this object, oh shoot, I'm not the master of the clicker today. If I want to get this value by simulation, I can do it the following way. So I can draw s values here, and then I'm going to draw my n values here. So I have this thing here, and I have this thing here. There's something really nice about this. What's really nice about this is that s and I don't interact. I only need to draw this s. I only need to do this simulation once. I don't need to do it for every single observation. So if you've got 200,000 people in your sample, that's a lot of time saving that you don't have to do that. So one really nice things about this thing that makes these kinds of methods much better computationally is that you can do the estimation once. You can get these things, and then you can simulate and you can simulate the model. So much easier to do. Another main advantage is with confidential data. Okay, and the advantage is, as many of you know, if you use confidential data here, if you want to run things on the Statistics Denmark servers, that's going to be very difficult. It's computationally difficult. You don't have to do that here. All you need to do on the Statistics Denmark data is get these things, and then you sit with your own machine and you do this thing with your own machine, and this is the part that's going to be hard. This is the part that changes with the value of theta. When you're maximizing the likelihood, it's this thing that you got to do. Now that's still hard. I mean, you're still solving that lots of times, but you can do that on your own machine. So that's a real advantage of these methods relative to maximum likelihood, which you can't do that way. Okay. Now I want to think about indirect inference, and I want to think about indirect inference in the following way. So think about the intuition behind this simulated method of moments estimator. What did I do? I took the sample average of this thing from the data. Now I'm going to take the sample average of simulated data that's simulated under a particular data generating process. Well, if the data generating process that I simulate from is the same as the true data generating process, I'm going to get the same answer for those two things. So that's the intuition of why that works. But as soon as that works, realize that it's much more powerful than just thinking about sample means. If I have the data generating process right, I can do whatever the heck I want to the actual data. If I do the exact same thing to the simulated data, I should get the exact same answer. So to me, indirect inference is generalizing this idea to be whatever the heck you want. Whatever the heck you want to do to the data, do the same thing to the simulated data, and try to make those things look like they're the same. Okay, I just said that. So what is the procedure that you pick an auxiliary parameter? So I'm going to estimate, I'm going to do the auxiliary parameter is whatever the heck I do to the actual data. I'm going to estimate that from the data, and then for any particular value of theta, I'm going to simulate the model, and then I'm going to simulate the data, and then I'm going to take the simulated data. Whatever I did to the actual data, I do the exact same thing to the simulated data. That's going to give me a b hat of theta that will depend on the parameter theta that I used for the simulation. Now I'm going to look for the value of theta that minimizes this function. Okay, so it's generalizing this idea, and it's going to be consistent because as long as you have the true data generating process, the simulated data should look the same as the true data, and should give you, and those two things should be the same. Notice that beta hat is whatever the heck you want to do to the data. It doesn't have to be correct. You don't have to the beta hat does not have to be the truly specified model. It does not have to estimate a causal parameter. It could be anything you want. It could be a regression coefficient where there's selection bias. Well, if there's selection bias in your regression, but you're also simulating the selection bias in your data generating process, you're fixing the selection problem. Okay? Where I'm headed, so where these things are coming together, is this has a nice connection with design-based stuff. In particular, I can use the design-based methods to get my auxiliary parameters. So examples of interesting auxiliary models, well, moments of regression things, misspecified MLE, misspecified GMM. You know, why do I do misspecified MLE? Because it's computationally feasible, so I do the wrong thing. But it's wrong in both ways, so I'm okay. But the most interesting ones to me are the bottom four, which are kind of the big four design-based things that I talked about before. So this, to me, is what's often giving you the best of both worlds. It's clear where identification is coming from. It's clear where identification of the key parameters are coming from. We're taking advantage of people that ran RCTs and came up with constructive instruments, but now we're using them to identify the parameters in the structural model. I'm going to show you a paper that does this. I mean, people have been doing this for a while, so I don't want to claim that this is certainly not new to me, and it's certainly not brand new by any means. People have been doing this, but I think it's an important wave of the future. I think it's a really nice way of bringing in the best of both worlds. Which, at some level, if you take that as the conclusion of what my conclusion from that's going to be the view. So it's sort of useful to think about maximum likelihood versus indirect inference, and I've had lots of arguments with lots of people that have strong opinions about which one is better. The advantage of some of it is how seriously you want to take your model. If you want to take your model really seriously and you say, my model is right, I'm sure my model is right, I'm 100% my model is right, estimate by maximum likelihood. That's going to be efficient, right? So it's going to give you the best estimate. So if you're in the view that either you believe your model or you don't believe your model, if you believe your model, go all in, MLE is the right thing. If you think, sometimes I've said things where I want to be on the fence, and I feel like I'm not being right on the fence here. If you want to think about a model as not actually being the model, but being an approximation to the way that the world works, then you might want to think about where identification of the parameters comes from. That one of the biggest things about the nice thing about MLE is, in some sense, MLE, if you want to say, is picking the estimator to be the best estimator in a statistical sense. It's going to give you the best estimates. Indirect inference, you're picking the auxiliary model. You're deciding which parameters it is that you put in. Okay? And in some sense, this is a good thing. There are good parts of this and bad parts of this. The good parts of it, the good part of it would be, I know what parameters I want to identify. I know what the crucial parameters are. I know kind of what they look like in the literature. I want to use this variation in the data to identify this parameters. Maximum likelihood, there might be something out in the tails that's happening that has really nothing to do with your model, that you don't care very much, but that might be really influential on the estimates. That might be really influential on the estimates you get. The other criticism would be, well, people are cherry picking. People are picking the moments they want to pick to give them the results that they want to get. Which is, we need to trust that people are going to be honest, but hopefully people will be smarter about picking things. It's also like another difference in MLE. I realize when I'm estimating MLE, I kind of wish I was doing indirect inference, and then when I'm doing indirect inference, I wish I was doing MLE. They're both hard, and they're hard for kind of different. They're hard for different reasons. Other differences, indirect inference, we talked about often it's there are cases where indirect inference is computationally feasible and maximum likelihood is not. There's just too many unobserved state variables to integrate over that you can't possibly estimate your model within your lifetime. We talked about confidential data. Indirect inference is easier. And I'm kind of thinking, but I'm thinking about simulated method of moments, and I don't know, some people might not like this. I'm thinking about simulated method of moments as a special case of indirect inference where the auxiliary parameters you're picking are moments. One objective of simulation estimators is that they often lead to non-smooth objective functions. Like if you're simulating you're simulating whether you're a fisherman or a hunter. Like you're either a fisherman or you're a hunter, and the only way you change that is jumping from being a fisherman to becoming being a hunter, which leads to that's a discontinuity in the objective function. My favorite thing, and maybe the thing that I like, that the highlight, why are we combining? In indirect inference, the map from the data to the parameters is much clearer, right? We can show you, you can see exactly what we're trying to fit in the data. So it's complicated because it's often many to many. It's not one to one, like you might have in an IV case. But it's much more transparent than maximum likelihood, which often it's hard to understand. Even when you're estimating the model by maximum likelihood, it's hard to understand exactly where identification is coming from. There's a bunch of issues with indirect inference. One is how do we pick the weights? And this is sort of a complicated thing. Like if you go to the optimal GMM thing, you're going to tend to pick the parameters that have the lowest standard errors, all else equal. But if you think about estimating these models, and some of your auxiliary moments are things like RCTs, and other auxiliary moments are things like means. Well, means tend to be much more precisely estimated than things like RCTs. So naturally, naturally you're going to put a lot more weight on the simple moments than you are on the RCTs. So you want to put more moments on the RCTs. How do you do that? And it's a little bit arbitrary. And that's another kind of discussion you can get into big arguments over beer about. And I'll show you this when I talk about the work that I did. Simulating from different, one nice thing about indirect inference versus maximum likelihood is that you can simulate from different data sets, right? You don't have to use exactly the same data set. Maximum likelihood is really hard if you have multiple data sets. A disadvantage, though, is you need to simulate the data generating process from one data set and the data generation process from another data set. And if the data is different, the data generating process is different. And getting exactly the data generating process, simulating that exactly, can be a pain when you're trying to estimate these things. Another really nice thing is you have these well-identified auxiliary parameters. So you have these RCTs that you're using to identify your model. You've got to put the RCTs into your model if you want to get your model to replicate the RCT, and you need to think about exactly what that means. Okay, so let me give you. So how much time do I have left? What? And when am I supposed to stop now? Oh, I have 5 minutes. I'm not going to give you this is a very broad overview of this paper. So it's a dynamic model of college. We want to understand how people go to college in the US and whether they graduate or not. We want to estimate this model. We're going to end up estimating this model. We're going to end up estimating this model by indirect inference. Here's the model. I'm just going to give you a broad overview of the model in one slide. People are going to graduate from high school. They have one decision. They basically have two different decisions in every period. One is whether they can either not go to college, they can go to a 2-year college, or they can go to a 4-year college, and they can do that each year. If they go to college, they take up loans. They take up loans from the Guaranteed Student Loan Program from the U.S., and that's it. When you have enough schooling, you get a degree, and the model is going to age at, we're only focusing on college decisions, not labor market decisions. The model either ends when you get a college degree or when you hit age 25, whichever happens to come first. We got lots of stuff in the model. So this model is relatively simple in the choice variables. it's relatively complicated set of things that we want to explain. So we're going to estimate by indirect inference, and we're going to use 4 different sources of data. One is we're going to be using the National Longitudinal Survey of Youth, which probably many people are familiar with. It's just a panel data set in the US that follows people that when they're young till they're older. Survey data set, lots and lots of different variables. So we're not going to use that to estimate any of the causal things, but that's going to give us the broad levels of education that we want to explain. So to give you, to motivate this just a tiny little bit, here's the broad data. I divided people into 5 categories, 5 mutually exclusively categories. Either you didn't go to college, you started a 2-year college and didn't finish, you got an associate's degree, you started a 4-year college and didn't finish, and you got an associate's degree. So the stunning thing here is the fraction of people that start 2-year colleges and didn't get a degree. Okay, and that's where we were interested in beginning this. The question is something like tuition subsidies going to help? To identify the model, we use 3 types of design-based things. The first we're going to call meta moments. That is, lots of people have estimated the effect of tuition subsidies on college. So you have like the Georgia Hope Scholarship, which gave free tuition to anybody that went to, as long as you had a good average in high school, free tuition to anybody that went to college in the state of Georgia. You can estimate the effect. You estimate the effect of going to college. You estimate the effect of finishing college. Lots and lots of well-designed studies on these things. Here, there are 2 surveys of this literature. We take a survey for the probability of starting and the probability of finishing. Notice, though, that it doesn't answer the question that I motivated before, which is what is the probability of finishing conditional on starting? Because starting is an endogenous variable. So we can estimate the effect on, we can estimate the probability of finishing, and we can estimate the unconditional, I'm sorry, we can estimate the probability of starting, we can estimate the unconditional probability of finishing, but that doesn't give us the probability of finishing conditional on starting. So to do that, we're going to use 2 different RCTs. This one is really nice because it waited until people were in college and then it randomly gave them a bunch of money. This is another one. It's not quite as nice because it waited until you were in your senior year in high school and then it randomly gave you a bunch of money. You hadn't quite made your college decision, but you had almost made your college decision. So it helps, but it's not quite as clean as the first one, but it's a much bigger, it's a much more generous policy, and it hits a broader range of people. Okay, so we're going to estimate that model by indirect. We're going to estimate the model by indirect inference, following these things. Let me just say, I want to say. I guess I'm out of time, but I do want to say, I wanted to say something, and I want to say something about what makes this hard. So I've been talking about how great this stuff is, and here's the challenge of doing this thing. So we have 3 different counterfactuals that we're looking at the data that we want to simulate, the meta moments and then the 2 RCTs. When we simulate our model, we need to estimate our model 4 different, we have to estimate the model, we have to figure out the dynamic programming problem 4 times. Like normally you do it once. Here, in the first case, you're doing it for the baseline. The second case, to get the meta moments, you're doing it where we increase tuition for everybody by $1,000. The third one is simulating the first RCT, and then the last one is simulating the last RCT. So we have to do it 4 different times. So it's 4 times slower than it would be if we weren't trying to do this. The other problem, and especially this last one, is goofy because we're giving it to people that are in their senior year of high school who applied to this grant. That's a very special set of people. So we have to redesign our model to get a sample of people that look like the controls in that sample, and it's a very weird looking set of controls. So we have to fit that and then also simulate that. So estimating these things can be hard. But what's the advantage of it? Well, the advantage is that once we've done it, now we can estimate the effect of a policy that's never been implemented in the U.S., which is, let's suppose we made tuition free at all U.S. colleges. What would be the effect of that on outcomes? You can see this as good news and bad news. It helps, right? College goes up. but it doesn't go up that much, right? This is a tremendously costly policy. And we're not making a big dent. And we didn't do anything at all to this thing. There's still a bunch of people that are going to two-year colleges and not finishing, okay? But at the same time, this is an advantage of the structural model is that for every single simulation of the data, I simulate that person twice. So I can see what they did in the baseline and what they did in the counterfactual. So so the way to read this is for anybody who was some 2-year in the baseline, this is where you end up in the simulation of no tuition. Okay, so the bad news is we don't the effect of the tuition policy on getting these guys to graduate from two-year college and get an associate's degree is zero. There's basically no effect at all. However, what the tuition subsidy does is it gets a bunch of these people that weren't going to graduate from two-year college, gets them to go to four-year college, and in fact, 10% of them end up actually getting a degree. Okay. So anyway, I'm out. Final thing, who benefits, right? So this is just, I'm dividing the same group of people into all the things that I had before, saying what is the value of tuition that's being given, that's being paid on behalf of this person in the counterfactual world. What are you going to see? The main people that benefit are the people that we're going to get BAs anyway. So the red lines are kind of the rectangles, and the blue lines are the triangles. So most of the money is going to people that were inframarginal. So you're not actually changing their behavior. You're just giving them money. You're giving money to people that we're going to get BAs anyway, which is relatively not that common in the U.S. So they were going to be doing okay, and they also tend to be coming from relatively wealthy families. So anyway, here's the conclusion. Arguments over which estimator is best. I don't think there's a best estimator. I think it depends very much on the question that you're interested in. There's some questions that you can't answer with design-based stuff that it's useful to use structural models. There are other questions that are much easier and cleaner to answer with design-based things, and you should answer those questions with design-based things. So to me, they're very much complements rather than substitutes. What I like about indirect inference is it makes that clearer. You're leveraging the design-based stuff to help identify the structural model, which you can use to look at counterfactuals that you couldn't look at without the structural model. It's not easy though. Like estimating these models, estimating these models, and particularly like incorporating these RCTs into the indirect inference thing. It was actually much harder than I thought it would be when I started. I hadn't really realized how complicated it was going to be to get that Nebraska thing into our structural model. I think this, to me personally, this is a promising future path that I hope everybody's on. Not that everybody's only doing indirect inference, but that everybody kind of sees the advantage of combining both the structural work with the design-based work. So that's it.